we've got people slowly crawling in. So we're going to go ahead and get this show on the road. So for those of y'all that are here, we're glad you're here. I'm excited about this. If you've been listening to our conversation, one, Kevin's just Kevin Boyer, and I'll let you do your own introductions. But just great guy in the industry, been around for a long time, passionate about this. It shows up in the way we were talking prior. And has been a longtime supporter of the MAC, and just really glad to have Kevin here. In addition to the work he's done, over the last you worked on the first edition, didn't you?
Mm-hmm. Yep.
Yeah, so you were there from the very beginning. Uh,
Yep.
so definitely glad to have you here and have your expertise. So without a further of ado, I'm going to turn it over to you, Kevin. Just some ground rules, right? If you have questions, please throw them in the chat. Kevin will have his presentation. We'll have about 15 minutes at the end to go over questions that y'all submit. And if we still have kind of a small group, we can open that up to a bigger discussion rather than chat, right? But for now, please mute yourself. Throw any questions in the chat. And Kevin, the floor is yours, my friend.
All right. Thanks, Dewey. I appreciate that. So I'm Kevin Boyer. I have been in the commercial pool industry now for right at 30 years. 100% of my time in the industry has been spent on the commercial side of the business. I have only ever worked for one group of companies, the Aquasol companies. Worked with Aquasol and with Aquasol's sister company, Poolshore, for all 30 of those years, really developing that entire company and the operations of that company. Today, Aquasol is still in the business of designing and distributing chemical automation systems and pumping systems for commercial pools that are sold around the United States and Caribbean. And Poolshore operates specifically in the southern United States from Phoenix all the way over to central Florida, with the bulk of our operations being in Texas and the company being headquartered in Texas. And Poolshore is first and foremost a supplier of water management services for commercial pools, where we deliver all of the bulk chemicals out to the pools, along with supplying a chemical automation system and all the tools necessary for the operator to operate a safe pool. And we also provide support services on those control systems. If they're needed by the operator, we'll come out and make the repairs, do annual PMs, change the probes, change feed tubes, those kind of things. In addition to that, we are a licensed commercial pool contractor in all of the states that we operate in, and we provide full professional repair and renovation services for commercial pools. And in addition, we teach CPO courses, are heavily involved, or as involved as we can be, in the Model Aquatic Health Code and the Center for Model Aquatic Health Code. Big supporters of the science-based nature of that program, and happy to help folks learn and give them the tools to operate their pools safely and efficiently. So what I wanted to present to you all today, maybe a little bit of a scattered presentation, but it's kind of a mid-season look at what are some of the things that we're seeing, things that typically pop up at mid-season that could be valuable reminders or interesting things to point out to pool operators that we're seeing, either something we see consistently or interesting things that are happening at this point. All right, well, good deal. Like I said, this is basically some operational reminders and interesting tidbits for pool operators that are now officially on June 17th in most places, in the thick of the summer battle of trying to keep the pools open and operating and performing well. So Some of the things that we'll talk about today, we're obviously in the time of high bather loads, high temperatures, what I call D-Day for the commercial pool season, and I'm sure a lot of y'all do too. July 4th is right around the corner. So today I want to talk about some simple actionable strategies and point out some things that we're seeing out there. One of the key focuses, and kind of where I started with this presentation before I veered off on a couple other paths, would be moving from resetting alerts, which is something common that we see with controllers this time of year, to doing a little bit more root cause analysis to try and figure out maybe what's behind those alerts. So that's a good starting point for today. And I want to kind of start by pointing out that alerts, and when I'm talking about alerts in this presentation, I'm really talking about alerts with the chemical control system. Alerts aren't normal, or they shouldn't be normal. They're a leading indicator of something that's gone wrong, a malfunction, or something that for the system to be operating correctly, it should be corrected at the root cause. A well-implemented and designed and maintained system should generally operate with minimum alerts so that when they do happen, they should be investigated. So first and foremost, I want to start out with what we call feed limit alerts. They may be called feed alarms. Others may call them overfeed alerts. But basically, these are designed to alert to feed system problems or undersized feeders. So essentially, they're adjustable timers that are going to warn when reaching the desired set point is taking too long. And in some cases, if it goes further, they may actually completely shut off the feed because they're assuming there's been a catastrophic failure based on the amount of time that it takes. Again, they can be set up as just alerts to kind of give an advanced warning on some systems, and others they're a hard stop. Some systems they're not adjustable, some systems they are. But if you know your controller, you can figure out the best way to utilize them to give you that heads up that something is wrong. Now, too often, especially in the case of undersized feeders, we often see operators just get into the mode of resetting them. So they think it becomes part of the normal operation, believe it or not. And the reaction to a feed limit alert is to unplug the controller, plug it back in to reset it, or with more modern controllers to press the clear or the escape button on the controller. But um, it's important that there may be a non-obvious feed problem that's preventing the controller from reaching the set point. And sometimes they can be really, really subtle. Sometimes it's not just an obviously undersized feeder for the demand of the pool. Little suction leaks in the tubing are a real common problem that can prevent the feeder from being able to, it won't stop it completely from feeding in all cases, but it'll slow it down enough to where it's not feeding rapidly enough. A worn feed tube, a worn diaphragm on a diaphragm style pump, a loose head on a diaphragm pump, even the beginnings of a clog at the injection point can all slow down the feed system and are definitely not normal, but they can all be figured out and resolved to get that system back to where it isn't constantly pumping. And kind of the analogy that I use for that is probably at one point or another, we've all had an air conditioning system in a house or in an apartment that it never quite seems to cool the room enough and it just runs all the time. Well, that's basically what's happening with a feed limit if you're just resetting it instead of getting to the root cause. And at that point, really, why even bother having a thermostat or why bother having a controller? Because it's not really able to control anything. So pH priority, and this isn't so much an alert as it is a feature, but this one I see coming up a lot. It's a feature that's in almost every modern pool chemical controller for the last 20 or 30 years. And a lot of operators that are out there think that this is to prevent acid and chlorine from feeding at the same time. And it's not. It's actually in a correctly flowing system. It's completely safe to feed acid and chlorine at the same time, and that's not why pH priority exists. We'll talk about interlocks a little bit later, which is the way you prevent unsafe feed into a system. So, what is pH priority exactly? Well, pH priority is very simply a way to prevent overfeeds of chlorine because of the inverse nature of the pH to ORP relationship. It's very simple once you've worked with it for long enough. I'm sure most folks on this call realize that a high pH lowers ORP and a low pH increases ORP, all with no change in the free available chlorine. So the end result of that is if the pH is higher than when the ORP to free available chlorine set point was established, when that correlation was made, that will cause the controller to overshoot the desired free available chlorine. So original versions of pH priority required the pH to reach its absolute set point before the ORP could feed. And that's still a valid strategy today, but other options are also possible, like setting a control band or hysteresis around the pH set point, or using only the high pH alert to interrupt ORP feed. There are all kinds of varieties of this and all kinds of different ways that it can be implemented as long as it's implemented, because it is a very, very important feature that keeps, number one, it keeps the free available chlorine closer to the set point band. And number two, it prevents it from running away. Now, if it does, quote unquote, run away, it'll eventually be stopped by the feed limit, but there can still be a significant increase that occurs before that feed limit kicks in if the feed pumps are sized correctly. If they're big enough to actually keep up, they can also be big enough to put in a little too much if you don't have this feature enabled. So I always recommend, it's not, the feature is built into just about every controller that's out there. I don't always see it implemented by the service company or the pool operator, but I consider it to be an absolutely essential element to a chemical automation system if you're using ORP to ultimately control a free available chlorine set point, which is the most common use for a chemical controller in the US. And just to point out again, any of these options for setting up pH priority, any of them will allow both the bleach or the chlorine and the acid to feed at the same time. But again, that's okay because we have other very, very important parts of the system that are designed to protect that. And speaking of that, I want to jump into that a little bit now. And it was the amazing part is these incidents have been going on for years and years and years, where an interlock on a system is either non-existent, or it gets bypassed, or it could be simply non-functioning. It could be broken. It may not be there. And in some cases, they get bypassed by the pool operators. And I want to be clear and say that most pool operators don't bypass these maliciously. They're doing it because they're under pressure to keep the pool open at all costs. And we can't operate that way. But just as I was putting this presentation together, there were a couple more incidents that happened just earlier this month. And so I took some clippings of them and added them here to the presentation. So on June 1st, there was a chlorine gas incident at a Nebraska water park. 8 guests to the hospital, impacted a total of 12 people. The really telling part to me is the part that I highlighted here, is that the exposures appear to have been associated with a routine filter backwash procedure performed throughout the day as part of normal water treatment operations. So what we know just by reading these two paragraphs of this story is that, number one, there was probably a significant root cause operational issue with this body of water that caused them to have to do a routine filter backwash during the middle of the day. Secondarily, we know that clearly swimmers were not removed from the pool when this incident occurred. There should never be swimmers in a pool if it's not circulating for a variety of reasons, including this. And lastly, we know that there was no functional interlock. We don't know if it was missing. We don't know if it was non-operational. We don't know if it was bypassed by the operator. We don't know by this story, but I added a little graphic. We worked with the Chlorine Chemistry Council several years ago to put together a training video that is now curated by PHTA, and this is just a little graphic from that shows what can happen. And this is, of course, a pool return line that has no water flowing in it. And so if you inject chlorine-based disinfectant into that line along with acid at the same time, of course, we're going to create chlorine gas. And that's exactly what happened here. And then, on this page, you can see that the gas bubbles get pushed into the pool and they bubble up and impact swimmers. And, the really bad part about it is chlorine gas is heavier than air, and swimmers' heads are typically right at the intersection of water and air. So unless there's a good breeze, the chlorine gas tends to congregate right there on the top of the pool, where people are more prone to breathing it in. So another one happened the very next day at a public pool in Ohio. They're calling it a mechanical failure. We had a pump fail. Our recirculation pump failed, but the chlorine pump did not fail. So there was still chlorine pumping out into a pipe. When the recirculation pump kicked in, the chlorine slug got shot out into the pool. So this is, again, that same type of situation. And this one is a little unclear as to whether it was just chlorine or whether it was chlorine and acid. My suspicion is that it was probably chlorine and acid, because that becomes an incident. Chlorine by itself does not always become an incident in every case. So this is another example where certainly we know something failed. They definitely had at least a partial circulation failure, but we definitely know that there either wasn't an interlock, it wasn't working properly, or it was bypassed. And we're just starting the season. We've already got 2 of these, and we've got a bunch of, I guess, 22 people so far this pool season transported to the hospital, which is just not good. I mean, this is supposed to be a recreation and exercise activity that really should be pretty low risk. All right, so how do you prevent this? Well, it's really, really, really very, very simple. All feed systems, with or without a chemical controller, and I say that because, believe it or not, there are still parts of this country and verticals where public pools that are open to the public may not have chemical controllers, but they may have feed pumps, and so or feed systems. And so any of these systems need to have an interlock, whether it's got a controller or not. Now, preferably, an interlock should be multi-layer. A lot of times facilities will have an interlock that ties the power to the feed system is dependent on whether the circulation pump is electrically powered or not. That may or may not work. It will work in cases where the circulation pump is intentionally shut down, but it won't work in cases where the circulation pump loses prime, or the water gets redirected for a backwash cycle or other things. So always recommend multiple layers of interlocks, preferably. And they can be a lot of different things, right? It's anything that is going to indicate that there is no flow at the point of chemical injection. So that's the other key with these interlocks is you have to be certain that at the point of chemical injection, if there's no flow, it's going to stop the chemical feeders from feeding, bottom line. And you can achieve that through the use of a flow switch. A pressure switch will do that. A current switch, and current switch should really only be one layer because, again, that's a way of sensing the electric current going to the circulation pump. Um, and there are in the Model Aquatic Health Code, the Model Aquatic Health Code did a really good job of spelling out all of the layers of protection and how they should be implemented. Um, and that is multiple layers of protection and challenge tested and logged every 30 days. So you know those layers are working. And it's a very simple thing to do. Uh, Turn off the circulation system, make sure the pumps, the chemical pumps shut off, put it in backwash, make sure the chemical pumps shut off. Very, very simple. And then, of course, the other bare minimum, they should never be bypassed, and no swimmers should be in the pool if it isn't flowing as designed. And there are multiple levels that you can go to with an interlock. Again, just a simple, as long as you have it and it's actually functional, a simple pressure switch, a simple flow switch, electrically interlocked, that works great. If you want to take it to the next level, there are devices that are available now that make it a little bit easier to retrofit a multiple layer solution onto a pool and will also automate and log that 30-day challenge testing. So there's a picture here of a device we make called the Advanced Universal Interlock, and it allows for pretty much any on-off sensing switch, up to 3 of them, to be on the input side. And then on the output side, it has relays that can directly control a chemical feed system and interrupt it. It also has dry contact outputs to feed into a chemical controller or feed pumps that have dry contact input. And then additionally, every 30 days, it will light up a warning light and prompt the user to start the test, shut off the circulation system, press the next button that validates that the pumps have indeed shut off, and then logs it, and it's good for another 30 days. And we're also building this same logic of multi-layer and 30-day challenge testing into our future chemical control systems. And I highly encourage other folks that are building chemical controllers to do the same thing. All right, so I'll get off my interlock soapbox a little bit. I'm very passionate about that. It's something that, if you heard Dewey and I talking earlier, it's something that just shouldn't be happening, that casts a bad darkness that just shouldn't be there on what should be a great positive industry. So something else I like to remind folks, when dealing with chemical automation, it really is a pretty simple concept, but we can tend to overcomplicate it from time to time as humans. Um, the vast majority of chemical controllers that are out there are using ORP to maintain a desired free available chlorine range. And so folks oftentimes get into a discussion of, well, where do I set the ORP? What's the right level? And I typically tell people, don't worry about it. You're making it too complex. You're trying to be a little too precise with that. The easiest thing to do is to balance your pool to your desired total alkalinity, pH, and free available chlorine. If you're using cyanuric acid, adjust it to the desired level. Then calibrate your pH probe to the test kit readings of whatever test kit you normally use. And then just adjust the ORP reading on the controller, the ORP set point on the controller, to whatever the current value is, whatever the current ORP value is. And that way you're just matching the free available chlorine in your pool with your other significant parameters taken care of, um, and achieve your set point that way. It's generally going to wind up being in the 650 to 800 millivolt range. If it isn't, that would typically indicate that the probe needs cleaning, replacement, or there may be some further chemistry investigation that's required. And you can make a case. I really prefer to see the ORP a little higher on the low end. I prefer like 700 to 800, with somewhere in the 720 to 750 being probably where 90% of them will fall in a typical outdoor pool, using bleach with some stabilizer at a normal pH reading. But the point is, don't overcomplicate the control. It doesn't have to be complicated, and the simpler you keep it, the easier it is as a pool operator to maintain it and keep it operating. So we're going through an absolutely massive shift right now in terms of how we're able to deal with data. And I know folks have a lot of different opinions on AI. Depending on the day, I have different opinions of AI as well. But the important takeaway for pool operators is get your systems online and get them reporting in so you at least have access to the data set, because we are at the point now where we can actually make good use of these data sets to understand what the controllers are doing, understand the chemistry of the pools even better, and approach things proactively for tuning the control of the pool. Not just the controllers either, daily tests with your test kit, or if you've even better got a connected test kit device, get this stuff all recorded to the cloud so that you have the data, because this is going to be the next big push that we're already really starting to see, but it's going to accelerate rapidly, is the ability to now actually use this data. And I know some operators have been collecting the data for years. I can remember back many years ago, some operators would have chart recorders where they would look at the little charts and try and figure things out. And now we can actually produce a chart that has the logging, and we can filter out certain events to make the log more usable. We can plot on that chart flow and pressure interruptions, all kinds of things. I'll show you some examples here in a minute. And it's a lot easier now. I know a big challenge a lot of times has been getting the internet out to the pool pump room. And up until the last couple of years, it was really, really tough in some instances because some of these pool pump rooms can be vaults that are really good at blocking signals. I know management, sometimes doesn't want to spend the money to run an Ethernet line out there. There have been all kinds of barriers, but now, because of where the cellular networks are at in this country, there are devices that are relatively inexpensive that basically are carrier agnostic. And so instead of worrying about, do I have service and which carrier do I need, you can get a carrier agnostic, essentially Wi-Fi hotspot, plug it in your pump room, and it will hop and it will find a carrier. And in most cases, you're going to be able to get internet now, whereas even just a few years ago, it was kind of a struggle, but it's gotten much better. And so I urge folks to get online where possible, because that data is giving us more and more insight and ability. And it's going to accelerate so far beyond even what I'm going to show you, that it's well worth being there. So some data sets, and this is just a very condensed summary. And this one would represent essentially good, consistent control. This is kind of what you want to see in a swimming pool. where your set point is 775, average reading 776, and the entire range is 769 to 784. No feet limit alerts, so that is really, really rock solid ORP control. pH set point is 7.5, average reading 749, range of 7.4 to 756, with 3 feed limits. And I should point that out. Feed limits, when you're evaluating those from what we talked about earlier, especially if you're running in pH priority, make sure that those acid pumps are large enough, because if you're running in pH priority and you're requiring the pH to get in range first, as you should be, you can have the opposite effect. If you can't do that quickly enough, you can wind up with your ORP dropping off before it can correct. So this is an example of it working really, really well and controlling well. There were 4 no flow events. We filtered out readings. So when there's no flow, I set this, I used AI to build this and the graphs I'm about to show you. But we have set this up to where it filters out for 1 hour around a no flow event, because we know that when there's no flow going across the probes in the flow cell, those readings are going to be wacky. So we want to take those out and not even show those in a graph. So here's what the ORP looks like for those. Here's what the ORP looks like for those numbers that I just showed you. And you can see that it just follows along with that set point real nicely. You can see exactly when the no flow alerts occurred. And you can see this is a pretty tight control range. I mean, honestly, I'd be happy with it even fluctuating further than this. This is the pH. And this is another example of it follows the control real tightly, indicates the pumps are sized correctly. There's no real feed problems. There were a couple errant feed limit alerts here, but they appear to be either fixed or not something that is happening on a continual basis. So this is representative of what I would look at and say this is data that shows an oversized bleach or chlorine feeder. 710 set point, 740 average reading. That's all pretty good, but it's trending a little bit higher than you could see the last one did, and it really had a pretty wide range on the control and no feed limits. So feed limits not the problem. It's not too small. And there were 6 no flow events that were filtered out. So here's what the data looks like on this one. You can see how everything is above that set point trend line for the most part. And that means this has gone the other way. And this feeder probably doesn't need to be quite as big as it is. Again, it's nothing to panic over. These numbers aren't terrible, but there is a little bit more fluctuation than I'd like to see ideally. Oh, and that same one has real consistent pH. A little bit low on the trend line, but again, relatively insignificant when you look at the scale that this is really from 7.6 to 7.4. So that's actually pretty solid, consistent pH control. So that's really just really scratching the surface on some of the things that we can really start to look at and analyze now by feeding very, very large data sets that would be difficult to analyze on the fly. And now we can analyze these almost in real time. And especially what I didn't show you here, but when you start adding in other data points to these graphs, like the test kit readings or the automated test kit readings, other items from electronic logs, you can really get a clear picture of how the pool is operating and know what to adjust or what to look at to tweak the performance of the pool. Couple reminders, now is the time of year to keep up with the critical chemistry. These two are probably the two that get forgotten about most. that can have the most impact on good, solid chemical control. Everything starts with the total alkalinity in the water. It is the building block for consistent sanitizer control. If your total alkalinity goes too low, it's going to drag your pH down. It's going to throw off the ORP to free available chlorine correlation and the set point. So really keeping that total alkalinity up and consistent is something to be monitored during the summertime, at least on a weekly basis. CYA, cyanuric acid. So it's not as much from my perspective about the absolute level. We can have hours-long discussions on that, but it's more about the consistency and that it's staying within that same range. So you don't want it fluctuating all over the place. I do like to keep it a little bit on the lower side. 20 to 30 parts per million is kind of my sweet spot, even lower sometimes. But if you do keep it under 30 parts per million, the other bonus that you get is there's no significant interference in the total alkalinity manual test, the titration test. So you don't have to go to the extra step of remembering to adjust for that. So just a couple fun, interesting tidbits to throw out there. These are definitely outliers, so I don't want to, as the old saying goes, I don't want to give you all a hammer and let everything start looking like a nail. But these two things are very interesting. They do happen from time to time. If you're using ORP to control free available chlorine, be very cautious when you're using non-chlorine oxidizers in your pool. There's nothing wrong with them, but you have to understand that the end result of using a non-chlorine oxidizer with an ORP controller is you will wind up with high ORP, because when you add that non-chlorine oxidizer to the water, it increases the ORP because it's an oxidizer, but it doesn't increase the free available chlorine. And so the controller thinks everything's fine, but meanwhile, the free available chlorine can go low or to zero, and there's no residual in the pool, and you can't figure out why you're not getting a chlorine reading, but the ORP is high. So be very cautious about using the shock and swim or non-chlorine oxidizers. At least recognize when you're using them. Another interesting tidbit, and we didn't really, I don't think anybody realized this until data logging, like the very first stages of data logging became more commonplace, because it's tough to notice because most of the pools aren't really being utilized at night. But there is an ORP to free available chlorine set point correlation error that can occur if you adjust your ORP to free available chlorine set point at night in pools that use cyanuric acid. Basically what happens is the ORP increases with no free available chlorine increase by as much as 75 to 100 millivolts at night. So it doesn't really hurt anything because when the sun comes out in the morning, everything falls back in line. There's typically, again, if your feed systems are sized correctly, there's not a lot of feeding that goes on at night anyway with the low usage. So it's not enough to let it drop out, and it catches back up again the next morning just fine. So the key takeaway is just don't make your ORP to free available chlorine set point at night to avoid issues from that. So I think somehow miraculously I pulled it in with, well, 16 minutes left for questions, comments, and anything we can help with. So Dewey, I'll turn the controls back over to you.
Great, thank you. So Kevin, I got one just right off the bat because I find the nighttime correlation interesting, right? In your data logging, do you see that effect when pools are not using cyanuric acid?
No, it is absolutely related to cyanuric acid.
Interesting.
And I will be completely honest with y'all. I am not a chemist. There was a very bright chemist in the industry by the name of Bob Lowry We had extensive conversations about it, and Bob could explain exactly what was happening, and did. But I'm too dumb to remember it. So all I can tell you is that the end result is, there's absolutely a correlation when the cyanuric acid is present, and don't make your adjustment at night.
That's interesting. I have heard that before, um, but I've never had the data sets to really dive into it and explore it. So, that's a good one. Good stuff. So, just a reminder, right? Throw chats in, throw your hand up if you want to ask a question. Well, we got Kevin on the phone. Kevin, I just got some interesting things, right? So, one is when we talk about interlocks, and y'all's universal interlocks, a great device, by the way. Great device. Love it. Um, I know in the Mac, we see a requirement that they're electrically interlocked to the pump as well. My question has always been, what's the reality of that, right? Do we see in the field a majority of controllers actually interlock to the pump, or do we see them just working off a pressure or flow-based interlock?
Well, that's actually exactly why we developed the AUI. We were having a planning and strategy meeting back in, I think it was late 2019, and we were discussing some of the changes to the latest revision in the Model Aquatic Health Code, and we really wanted to start dog fooding the multi-layer approach. And the reality is that the first layer of that, the electrical interlock, really only exists on modern pools that have been built in maybe the last 4 or 5 years, and really only in the aquatics vertical. And what I mean by the aquatics vertical, the bigger pools, the YMCA's, the municipal pools, usually water parks, really anything that has been designed by an aquatics engineer. Those always have built-in electric interlock, and so it's really easy to achieve the multiple layers. Not necessarily the challenge testing, but the multiple layers are easy to achieve on those pools. However, uh, those aren't the majority of commercial pools in the U.S. The majority of commercial pools in the U.S. are hotel pools, motel pools, apartment pools, all these little commercial pools that are out there. And fortunately or unfortunately, they're often built by design build type companies, a lot of them residential pool builders, and they just don't do that. And retrofitting that afterwards can be kind of expensive to get an electrician in to actually tie that all together. And so that's a big part of the reason we developed the AUI, was to have a retrofittable solution for those pools, or for any pool that didn't have that first layer interlock already built into it, where you could just add a current switch and let that current switch feed into the AUI, and then add your second layer as we like pressure switches. You can use flow switch, whatever. But that was exactly what started us down the path of building that device, was the realization that this is a path we want to head down, is the multi-layer approach, but how do you actually achieve it without it being very expensive?
Yeah. And I think that last one was a good note. That's a relatively inexpensive way to be MAC compliant and to have that electrical interlock. So, and I wonder, some of these other pools that you talked about at the very beginning, right? If they had this, advanced interlock installed, because they weren't designed properly, they weren't built properly for whatever reason, how much of that would have solved some of these issues?
Yeah, that's a great question, and that's the question that keeps me up at night, to be honest with you.
Yeah, yeah,
Yeah.
absolutely. Absolutely. Well, does anybody have any questions for Kevin? Going once. Going twice. Okay. Well, good stuff. Kevin, man, I appreciate you. I appreciate you for coming in and being the flag bearer for this. You have for a long time on Interlocks and, and preventing these chemical injuries. And just on behalf of the industry, I just want to thank you for toting that line and being that vocal advocate for your pretty much entire career. So if you're late to the party and you missed some of this webinar, or you want to send it to others that weren't here in the next week or so, we will have this up on our YouTube page for visibility and posterity. And it's really good stuff. And again, Kevin, thank you so much. Everybody's Hill, we're halfway through summer in the deep south. And then for some of y'all, you're just getting started. So folks, y'all keep them safe, keep them healthy, keep them safe. And we'll see you next go round. All right. Thanks, Kevin.
Thanks,
Thank you, everybody.
guys. Bye.